Hello students, in this lecture we'll discuss Euler's function, what is Euler function, Euler theorem and Fermat's theorem. So let's define what is Euler's function phi. For any positive integer n, phi n is defined as for n is equal to 1, phi 1 is equal to 1. And for n greater than 1, phi n is equal to number of integers less than n and relatively prime to n. Number of integers phi n. What is phi n? Phi n is the number of integers less than n which are relative and relative prime to n. So let's give an example to show what is phi n. Suppose n is equal to 6, which is greater than this n, which is greater than n, phi n. So phi n is this, n is 6, so phi 6 will be equal to 2. Why this is 2? Because when if n is 6, then the number 5 and 1 are relatively prime to 6. Means the greatest two numbers relative prime if their greatest common divisor is 1. So if you divide 6 by 1, 5 gives 1. If it's 6 by divided by 1, greatest value will be 1. So these two numbers 5 and 1 are relative prime to 6. Therefore, so how many integers are less than 6 which are relative to 6? They are only 2, 5 and 6. So 5, 6 will be equal to 2. Now, if n is a prime number, so prime number are those numbers which are divisible themselves or by 1. So either p is divisible by 1 or p is divided by this p itself. Therefore, phi p for this will be p minus 1. Example for this is if p is a prime number, then all the integers less than p, that is 1, 2, 3, p minus 1, are relative prime to p. So therefore this value is phi p is equal to p. An example for this is if p is 7, 7 is prime number. So all the numbers less than 7, 1, 2, 3, 4, 6, 1, 2, 3, 4, 5, 4 to 6 are relatively prime to 7. Therefore, means this one is 1 and 7 is equal to 1, and 2 and 7 is equal to 1, 3 and 7 is equal to 1. This goes as 4 and 7 is equal to 1, 5 and 7 is equal to 1, and 6 and 7 is equal to 1. So these numbers are relative prime. These numbers are relative prime to 7. Therefore, phi 7 is equal to 6. Now, if it's any positive integers and this is a large number, so we can factorize into different product of different prime numbers with the indices. So p1, p2, pk are distinct primes numbers, and alpha i's are natural numbers. Alpha 1, alpha 2. Then phi and 4, that will be equal to n into 1 minus 1 from p1 into 1 minus p1 from p2 into 1 upon into 1 to 1 minus 1 from p2. Example is, suppose p is equal to 3600. So if we factorize them into prime factors, we'll get 2 to 4 into 3 to the power 2 into 5 to the power 2. The product will be equal to 3600. Now, what will be how many numbers are prime to 3600? Less than 36 will be 3600 into 1 minus 1 of p1, p1 into 1 minus 1 of p2 into 1 minus 1 of p3. So if we simplify this, we'll get our answer will be and multiply them with 960 numbers less than 3600 will be relative prime to 3600. So we can find it. Now next we put the Euler's theorem. If n is a prime number and a is any integer such that in any integer in positive number such that A and N are relative prime. A and N are this greatest common divisor of A and N are is equal to B, and N is greater than 1. Then A is for phi N is congruent to 1 modulo N. So this is, let G is the set of all those integers are which are relative prime to N and are less than 1 and greater than 1. Less than N and greater than 1. So what does mean? What is this? This is G is the set of those integers which are less than N and relative prime to N. The set of integers. Therefore, G is a group under multiplication module, and G is a group under multiplication module N with identity element 1. So, what is this? Then order of G will be equal to order of equal to phi N. That means phi N. So, two cases will rise when N is equal to 1. N is equal to 1, then phi N is equal to phi 1 is equal to 1. So, if we replace phi N by 1, A is for phi N is congruent to 1 modulo 1. So, this is equal to, this implies if it's equal to phi 1 here, this is equal to A 1 is congruent to 1 modulo 1. What is the meaning of this? This means 1 divides A minus 1. It's 2. 1 is the divisor of every integer. This is true. The result is true for A of phi is equal to congruent to 1 modulo, and this is true for N is equal to 1. Now, the second case is when N is greater than 1. Greater than 1, and A is an integer. A is an integer, positive negative. And we divide A by N. If we divide A by N, then by division algorithm, there exists quotient and remainder. Q1 and R1. The remainder will be less than N, it is equal to 0, such that A is equal to N Q1 minus R. Now, if again two possibilities, if R1 equal to 0 means N is completely divisible by A is completely divisible by N. So, if R1 equal to 0, this implies A is equal to NQ. What does this imply? This implies N divides A, and N divides N, and divides itself. So from this, if N divides A implies the greatest common divisor of N and A will be N. What is implied? Greater than N. So this will be N implies greatest common divisor of 1 and N is equal to greater than 1. But given is greatest common divisor of 1 and N is 1. So we have supposed that R1 equal to 0 is not true. Its contradiction implies R1 will not be equal to 0. R1 will lie between 0 is less than R1 less than 1. So if 0 less than R1 less than N, then the remainder when we divide A by N is R1. So let us suppose that the remainder when we divide R1 by A by R1, R1 and A N, the greatest common divisor of the greatest is equal to N. So this implies M will divide R1 and M divides N. So substitute the value of R1 here because R1 is not equal to 0, so R1 equal to A minus NQ. So this implies, when you substitute the value of, this implies M divides A minus NQ1 R1, and M divides N implies M divides N into Q1. So if M divides A minus NQ1 and M divides A NQ1, so M will divide the sum. So M divides A minus NQ1 plus NQ1, and M also divides M. So when we cancel them out, we got M divides A and M divides N. This implies M divides the greatest common divisor of A and N. But the greatest common divisor of A and N is equal to 1. given. This implies m divides 1. M divides 1, so for if m divides 1, so m must be equal to 1. Therefore, the greatest common divisor of R1 and n is equal to 1. And R1 is less than equal to, 1 is less than equal to R1 less than n. What does this imply? This implies R1 belongs to G. And A is equal to NQ1 plus R1. Plus R1. So, what does this imply? This implies when we divide A by N, the remainder is R1. So, we can write it as A is equal to R1 modulo N. And A is equal to R modulo N, and therefore A is for phi N. Means N divides A minus R1. This implies N divides minus R1. So, if N divides A minus R1, then M will divide A is power phi N minus. So, if A is power phi N minus A power R1 is power phi N. And also do this. If N divides this, then this implies A is power phi N is equal to R1 is power phi N modulo N. What is this? Now, R1 is for phi N is congruent to 1 modulo N. R1 phi 1 is congruent to 1 modulo N. Because R1 belongs to G implies R1 is power out of this is equal to an element. R1 out of G is equal to R in G implies this implies N divides this implies N divides R equal to phi N minus 1. So when this implies R1 is equal to 1 in G, what does it imply? So this implies when substituting R1 here 1 is equal to A of phi N is coming to 1 over N is equal to. Now next one is for next one. If P is any positive integer A, if P is any positive integer and A is any integer, then A is power P is congruent to 1 mod to P. What is this mean? What's the meaning of this? This implies P divides A is power P minus 1. Proof. Let me show that P divides A per P n minus 1. This implies P A per P is coming to A mod to P. Given is what is given? P is a prime number and it belongs to is integers. Two cases will arise. Either their and the greatest common divisor of A and P is 1 or greater than equal to 1. Greater than 1. So if the greatest first case, if the greatest common of A and P is equal to 1, then by Euler's theorem, A raised power phi n is equal to 1 over phi n equal to phi n power P is prime number is equal to A power P minus 1 is equal to 1 over since P is prime number phi n. What is implied? This implies P divides A raised power P n P minus 1. If you divide if P divide this, there is a quotient K and remainder 0. And we can write A is power P minus 1 is equal to Pk and remainder 0. Multiply both sides by A. So we got A is power P minus A is equal to APK. APK, what implies? It implies A will divide this, P will divide this, and K will divide this. But we'll proceed toward our proof of the theorem. So we'll only consider P divides. If this is the product of these numbers, then these number each of the number will divide this, but implies P divides A power P minus 1. This is again implies if this divide this, then in then in modulus form we can write A power P is equal to A modulo P. Proof for when A and P are reciprocal. Now, if A and P are not reciprocal and greatest common divisor of P and K is greater than 1. Since P is a prime number, therefore divisors of P are 1 and P. divisor of A and P are 1 and P. If greatest common result of A and P, let us suppose is equal to 1, D, sorry, D, which is greater than 1, we are discussing for the greater number. Now, if the greatest common divisor of A and P is D, this implies D will divide A and D divides P. If D divides A and D divides P, and P is a prime number, so D must be equal to P. So what does it imply? It implies the greatest common of A and P is equal to P. Implies P divides A and P divides A to P. If P divides A, P divides P, then P divides A to P minus A. This implies A power P is common to A mod of P. Completes the proof for P greater than 1. Thank you very much.